Morning, everybody. I'm Dr. Swathika, Assistant Professor from the Department of Biochemistry. So today we'll be dealing with enzyme assays. So before going to enzyme assays, we need to know how to define enzyme activity. So why we need to do enzyme activity, all these things. So physical properties of an enzyme is most commonly measured by relative rate by which the substrate has been converted to product. So 1 unit activity is equals to 1 international unit. So it is the amount of enzyme which converts 1 micromole of substrate to product per minute at 25 degrees Celsius. So what is 1 international unit? It is the amount of enzymes which will convert 1 micromole of substrate to product per minute at 25 degrees Celsius. And if you have to determine the specific activity, it is international unit of enzyme activity per milligram of total protein present. Okay, so that is the specific activity of enzyme. So what are enzyme assays? Enzyme assays are basically laboratory methods which can measure the enzymatic activity. So they are mainly important for the study of enzyme kinetics and enzyme function. These are the most two major fields where we need to do enzymatic assay. So what is meant by an assay? An assay is the act of measuring how fast a given or an unknown amount of enzyme will convert substrate to product. So it is basically the act of measuring a velocity. Enzyme assays measure either the disappearance of substrate over time or the appearance of product over time. So an assay will be required to determine the concentration of a product or a substrate at a given time after the reaction has been initiated. So how are we going to measure the enzyme activity? Enzymes are usually present in very small quantities in all the biological fields. Since they are present in very minuscule amount, we could not measure directly the enzyme concentration. Rather than that, we measure the catalytic activity of the enzyme, which is an indirect measure of concentration. We measure how much the work it performs, the catalytic activity, which means the rate at which it catalyzes the conversion of substrate to product. So the enzyme activity here will reflect the concentration of the enzyme. We determines that activity is proportional to concentration. So what are the types of enzymes assay? Enzyme assays can be basically split into two groups according to their sampling method. First one is the continuous assay and second one is the discontinuous assay. So what are continuous assays? Continuous assays are nothing but where the assay will give a continuous reading of activity. So we need to make multiple measurements, usually of the absorbance range, are made during the reaction. That is, we are measuring the change in absorbance at multiple time intervals during the reaction time. So either it will be measured at specific time intervals which are fixed, usually from 30 or 60 seconds, or it can be measured continuously by continual reading spectrophotometry. These assays are basically advantageous over fixed time methods because the linearity of the reaction may be more adequately verified. That is, since it is going to be measured continuously, we can measure the linearity. That is, once we increase the concentration of the enzyme, how much in the rate of reaction can be measured. That is what we call it as discontinuous assays. These are assays where samples are taken and the reaction is stopped and then the concentration of the substrates or products are determined. So here what happens, the reaction will be allowed to proceed for a designated time interval and then the reaction will be stopped by either inactivating the enzyme with a weak acid and the measurement is made for how much amount of the reaction that has already occurred. So what are the detection methods for the enzyme-based assays? Here we can see so many methods. First is the spectrophotometric method. Second is the sampling method. Third is the electrode method. Fourth is manometric method. Fifth is polarimetric method. Sixth is fluorescence method. So what are the features of a good enzymatic assay? So these are the 5 basic features we need for an enzymatic assay to fulfill the required criteria. That is, it must be simple, it must be specific, and it must be rapid. So we need not wait for the hours or weeks for the results to appear. And it must be sensitive. That is, a very minute amount of sample is needed. And it must be easy to use, and it must be economical. What are continuous assays? Deduction method. The first deduction method is by spectrophotometric. Spectrophotometric assay is the most commonly employed method of deduction in enzymatic assays. So here what happens? They use a spectrophotometer, a machine which is used to measure the amount of light a substance can absorb and to combine kinetic measurements and Beer's law by calculating the appearance of product or disappearance of substrate concentration. That is, what do they say is that basically in spectrophotometer, we are going to measure the amount of light the substance can be absorbing. So whatever reaching the transmitter will be like excluding the amount of light which will be absorbed by the substance present in the cuvette. So it will combine both the kinetic measurements and Beer's law by calculating the appearance of product or disappearance of substrate concentration. So if the light is in visible region, we can actually see a change in the color of the assay. These are called as polarimetric assays. If UV light is used, and the common enzymes which will be employed in case of UV lights usages NADH and NADPH, which will absorb UV light in their reduced form, but do not in their oxidized form. These are the reduced form, that is NADH and NADPH. Their oxidized forms are nothing but NAD for NAD and NAD. So most of the substrates and products of multiple enzyme reactions will absorb light either in the visible region or in the UV region. So mostly the spectra of substrate and products will not necessarily be the same. Hence, what we can use is we can make use of this advantage, and the conversion of one into another, that is the substrate and the product, is followed by a considerable change of absorption, and by measuring this change, the progress of the reaction can be followed quantitatively. Enzyme will be allowed to react with the substrate. The decrease in concentration of the substrate or the increase in the product produced will be followed thereafter spectrophotometrically. So next, what are the advantages of spectrophotometric deduction is that here you can see the picture of a spectrophotometer, and in the left side, and on the right side the pathway through which the light is going to go through in the spectrophotometer. That is, from the light source, we have it passes through a wavelength selector where a particular or a desired wavelength has been selected, either in the visible range or in the UV range, based upon what we are going to measure. Then this wavelength of light is allowed to pass through the sample, and here what happens, based on the concentration of the substance present in the sample, light absorption occurs, and the remaining light will reach the detector, which will be connected to the computer, and a digital will be converted into a digital analog signal. Either we measure the transmittance or we measure the absorbance. The advantages of spectrophotometric deduction are: it is easy, simple, it is sensitive, and it requires very small sample, and the whole progress curve can be followed quantitatively. So cases in which the products will absorb but not the substrate. So like either we are going to see the change of the appearance of product over time or disappearance of substrate over time. So here in this case, appearance of product over time was seen because the product will absorb light but not the substrate. So this includes enzymes which catalyze the addition of goods to double bonds or the reverse reaction. Like here you can see fumarate will absorb light at 300 nanometer. That is UV light at around 300 nanometer, which can be converted into malate with the help of enzyme fumarate hydrolase. But malate will not absorb light. So similarly, U rate, which will absorb light at 290 nanometer in the UV region, but it is a product. So here what happens, hypoxanthine needs to be converted to urate with the help of xanthan oxides. So the appearance of product over time could be measured because urate is easily measured at 300 or 90 nanometer. The decrease in absorption at 300 nanometer indicates that the reaction is moving in a forward direction and in first case, and the increase in absorbance at 290 nanometer in the second case. Next, the coenzyme will undergo change in absorption or reduction or oxidation by the substrate. So here you can see NAD plus, which is the oxidized form, will get converted into the reduced form NADH, which will absorb UV. Similarly, NAD plus, which is the oxidized form, can get converted into NADPH, which is the reduced form, and both these will absorb light at 340 nanometer. And the third example, where FAD plus has got higher absorption at 450 nanometer, which can be reduced, converted into FADH2, which is the reduced form, which has got much less absorption at 450 nanometer. It is totally different from that of the previous two examples. So here same thing happens. Upon pyruvate to lactate conversion, we have conversion of NADH to NAD plus. NADH will absorb light at 340 nanometers, so there will be increase in absorbance, or NAD plus there will be decrease in absorbance. So decrease in absorbance per minute can be used to measure the rate of LDH activity. So again here glucose 6-phosphate can be reduced or oxidized converted into 6-phosphogluconolactone, during which the coenzyme NAD plus will be reduced to NADPH. Again, NADPH, the reduced form will absorb light at 340 nanometer, but not the NADP plus. Hence, what happens? There will be increase in absorption at the end of the reaction, which will measure the activity of glucose 6-phosphate dehydrogenase. Again, next will come to coupled reactions. What are coupled reactions? So, in many reactions, changes in substrates or products cannot be easily observable by spectrophotometric methods because they do not absorb light. So, in such a case, where such an enzymatic reaction which does not result in change in absorbance of light, we can still use a spectrophotometric assay for the enzyme by using a coupled assay. Here what happens, the reactions which can be measured can be coupled to enzymes that can be detected via spectrophotometer. So the product of the reaction which could not be, which needs to be measured, can be used as substrate of another easily detectable reaction. So here you can see a coupled assay where this is a reaction which is happening in citric acid cycle. Citrate will be converted to isocitrate. This is a reversible reaction under the influence of acronitase. We need to, so at the assay mixture, we need to detect the activity of isocitrate dehydrogenase. But this isocitrate is a product which is formed and it serves as a substrate for the next reaction. So it is converted into isocitrate dehydrogenase. It converts isocitrate into alpha ketobutyrate, during which NAD plus is reduced to NADH. So by this way, we can measure the amount of isocitrate. Similarly, phosphoenol pyruvate to pyruvate conversion and pyruvate to lactate conversion are brought about by the enzymes pyruvate kinase and lactate dehydrogenase respectively. So here what happens, both ATP and ADP will absorb light at 260 nanometer in the first reaction. So we could not easily differentiate. So what happens, this reaction will be followed by pyruvate to lactate conversion, where there will be big increase in absorbance at 340 nanometer, which is specific for NADH. So upon pyruvate to lactate conversion, there will be decrease in absorbance. The second method of reduction is fluorescence method or fluorimetric method. Fluorescence is when a molecule emits light of one wavelength after absorbing light of a different wavelength. So it basically uses a fluorometer. Fluorimetric assays use a difference in fluorescence of substrate from the product to measure the enzymatic reactions. Or basically the flavin compounds, which includes FAD plus and FADH, will fluoresce in reduced form and lose their fluorescence in oxidized form. So an example of these assays is use of nucleotide coenzymes NADH and NADPH. So here the reduced forms of fluorescence, whereas the oxidized forms are non-fluorescent. So oxidation reactions can there be followed by a decrease in fluorescence, and reduction reactions will be followed by an increase in. So this fluorescent method detection is more sensitive than spectrophotometric assay, but can basically suffer from interference, which are caused by impurities, which will also fluoresce, like it will also fluoresce and will interfere with the fluorescence of the substrate of the right. And the instability of many fluorescent compounds upon exposure to light is another major disadvantage in fluorimetric detection. The advantages is that it is detected in small quantities. This even in a small amount of substrate or product, it can easily detect the quantitatively, and it is non-dangerous, non-hazardous as compared to radiometric detection. The third method of detection is calorimetric. This calorie is different. The first we did the spectrophotometry is polarimetric based on color. Here it is based on heat released or absorbed by the chemical reactions. These are very general because in most of the reactions there will be a change in heat which can be measured. So these assays can be used to measure reactions that are impossible to assay in other ways. The fourth method of detection is chemiluminescence, which is the emission of light by a chemical reaction. So some enzyme reactions will produce light, which can be used to measure product formation. These type of assays are very sensitive since the light produced can be captured by a photographic film over days or weeks. But it is very hard to quantify because not all the light released by the reaction will be detected. That is luminescence. There is an emission of light upon chemical reaction. That is what we call it as chemiluminescence. The fifth mode of detection is by manometric method. It is here it uses a manometer, and these are most convenient and accurate methods for the following reactions in which one of the component or a substrate is a gas. So it is used basically for the study of oxidases, which will measure the oxygen uptake, and study of decarboxylase, which will measure the carbon dioxide. Emission or absorption of gas is basically measured by Warburg manometer. The sixth mode of detection is electrode method. Electrode method, here what happens, to follow the reaction which involves the production of acids, we use electrode method of detection. Basically, they use a glass or a platinum electrode. Hence, here we can see an example of pH meter, where it is used to measure the change in H plus concentration. So during enzymatic reactions, there will be a change in pH. So as the reaction proceeds, it can also be used be detected by electrode method. The seventh method of mode of detection is polarimetric method. Polarimetric method basically uses a polarimeter. So for one isomer which can get converted into another isomer, it will change the direction of rotation of a plane polarized line. So this polarimetric method is basically used for substrates which are optically active and will get converted into an optically inactive or vice versa. So it can be used if both substrate and products are optically active but different in their specific rotation. That is, it can not only measure conversion of an optically active substrate to optically inactive product, or optically inactive substrate to an optically active product, but also if both are optically active, both substrates and products are optically active, but if they differ in their specific rotation, it could also be detected. Like for example, D-glucose, which is the substrate, getting converted to L-glucose, which is the product. Both in this case are optically active, but the rotation direction differs. Similarly, sucrose, which upon hydrolysis will give D-glucose and E-fructose. Discontinuous assays. Discontinuous assays are when samples are taken from an enzyme reaction at intervals, and the amount of product production or substrate consumption is measured in the samples by different chemical methods. The most commonly used method in a discontinuous assay is radiometric method, which measure the incorporation of radioactivity into the substrates or it's released from substrates. Either they measure the incorporation of radioactivity in the substrates or the release in the substrates. So the radioactive isotopes which are most frequently used in these assays are C14, P32, S35, iodine 125. Since radioactive isotopes can allow the specific labeling of a single atom of the substrate, that is, if the substrate has got so many atoms, out of which we are going to radio label only the carbon atom, it can basically label only the carbon atom. Since it can specifically label a single atom, these are very sensitive and specific. And they are frequently used in biochemistry and often the only way of measuring a specific reaction in the case of crude extracts. And the radioactivity is usually measured in this procedure using a scintillation counter, which measures the ionizing radiation. It is very sensitive method but very hazardous. So we are not using it. Next method of detection in case of discontinuous assays, chromatographic method. Chromatographic assays actually measure the product formation by separating the reaction mixture into its constituents or components by chromatography. This is basically done by high performance liquid chromatography, but can also be used using a simpler technique of thin layer chromatography. But this approach is very tedious and it needs a lot of material. Sensitivity can be increased by labeling the substrates or products with a radioactive or a fluorescent tag, which are the most sensitive methods. With this, I will end my PowerPoint or class on enzymatic assays. Thank you.